Okay, so this is a short video on the calculation of gas law. Okay, in your exercise, I'm going to show you two examples of the calculation of gas law. Okay, so to do this question, first you have to understand the pressure in fluids. Now, when I say fluids, it can mean gases or it can mean liquids. Pressure in fluids depends on the depth. The more the depth, the higher the pressure. Okay, so let's say I am at 10, okay, let's do 5 meters below the water surface. At this point, let's call it point A. If I ask you, what is the pressure at point A? We take the depth of the water. Okay, you have to also know what is the medium. This medium is water, right? Is water. So I would take the depth, which is 5 meters, and then the medium, water. So I will call it 5 meter H2O. That is the pressure at point A. Okay. Now, the total pressure acting at point A is not only from the water. You have to add the weight of the atmosphere as well. The air above it has a pressure. That's atmospheric pressure. Okay. Atmospheric pressure, we fix it at 76 cm/Hg. There are a few units. This is the first one. And we have 1 × 10⁵ Pascal. We have 760 millimeter Hg. And we have 10 meter H2O. You can see we have many different units of pressure. cm/Hg, Pascal. This is the one that we are familiar with, right? Pascal. And we have mmHg, H2O. Okay? Because atmospheric pressure, the atmosphere has a weight. Pressure, the way you think about pressure is like this. If you're at this point, then whatever is sitting on top of you has a pressure pressing on this point. So pressure is actually due to the weight of the water pressing on this point, and also the weight of the atmosphere pressing on this point. So if I ask you the total pressure acting at point A, it is 5 meter H2O plus the atmospheric pressure as well. So which one do we choose? Because this is water, so you have to choose the same one, water, 10 meter H2O. Okay, so this one, we plus 10 meter H2O equals to total 15 meter H2O. That is my total pressure acting at point A. If let's say I'm under the Mercury Lake, like a Mercury Sea, same height, sorry, same depth, 5 meter. Then what is the pressure at point B here? Okay, then I calculate, but I use a different unit because this is a different medium. Pressure at point B equals to depth, 5 meter. Okay, we just take the depth, the length. 5 meter mercury, right? So I will write Hg, stands for mercury. 5 meter Hg, that's 500 cm Hg, right? And don't forget the atmospheric pressure. So we plus, which one do we choose? The first one, 76 cm Hg. So total pressure is 576 cm Hg acting on this point B here. Okay, so in the question, you see a lot of cm/Hg or cm water, meter water. All these are the unit for pressure. So pressure can take 4 different units. Okay, now let's look at the question. Question 20. The diagram shows a diver swimming 90 meters below the surface of the ocean lets out a small bubble of air from his mouth. If the volume of the air bubble from his mouth is 50, Okay, meaning that the moment that the air bubble is produced, the volume V1 is 50 millimeter cube. And pressure P1, what is the pressure acting at the bubble? That depends at the depth when the bubble is emitted. What is the depth? 90 meter below, right? 90 meter below the surface. So pressure acting on the bubble is 90 meter water, H2O, plus, what is the atmospheric? Here, it's given here. The atmospheric pressure is 10 meter water. So plus 10 meter water, H2O. So you get total is 100 meter H2O pressure pressing on the bubble. Okay, and then this bubble rises to the surface of the water. Rises to the surface where the depth is now 0. So what is the pressure acting on the bubble when it is at the surface? P2. So P2 is only the atmospheric pressure because 0 depth, there's no water pressure. All the pressure comes from the atmospheric of the air. So P2 is 10 meter water, H2O. Okay, 10 meter H2O. And then V2. You want to find this, right? Okay, and the bubble here and here, the size is different. The bubble at this depth is very small because the pressure is very large. So it compressed the bubble. And the bubble, as it rises, the volume will increase because the pressure decreases as it comes up. Okay, then you can find using your Boyle's law, right? So we are going to assume that temperature does not change. P1 V1 equals to P2 V2. Okay, what is your P1? 100 times into V1, 50. And then equals to P2, 10. And times into V2. You don't need to worry about the unit because the unit will cancel out each other. Okay, meaning that you don't need to change to SI. You can just use mm cube and you can just use meter H2O. Both sides, they will cancel out. Okay, so 100 times 50 divided by 10. V2 is 500. Use the same unit, mm power 3. That's the answer for V2. Okay, now we look at second example. Figure 14 shows a gas trapped by 4 cm of mercury in a glass tube. Later, mercury is added into the glass tube until the length of the gas trap becomes 7 cm. So initially it's like this. This is the mercury length. This one, the length of the mercury, we set the length of the column. Okay, so the length of the mercury column is 4 cm. And the length of the trapped gas is 8 cm initially. And when you add mercury, the length increases. Then it says that the trap A becomes 7 cm, right? 7 cm. What is the new length of the mercury column? You want to find this mercury column length, X. Okay. Same, we take the pressure. Now, here the trapped gas is under the mercury, right? If I ask you, what is the pressure acting on the trapped gas? Here. The point directly underneath the mercury column. Here. What is the pressure acting here? It equals to the weight of the mercury and the atmospheric pressure above the mercury column. Okay, so if I want to find the pressure at this point, let's call it point A. PA equals to the length of the mercury column, 4 cm Hg. Why I put Hg? Because this is mercury column, right? If it's water, then it's H2O. So in other words, this is like the depth, just like the mercury lake. Okay, this is the depth. Depth here, and then I plus the atmospheric pressure above. It is also pressing down on the same point, right? So I plus, what is the atmospheric pressure? Given here, 76 cm Hg. So 76 cm Hg equals to 80 cm Hg. That is pressure initial. So that's P1 on the gas, the pressure of the gas. Okay. So how about volume? V1. Volume, because it is like a tube, right? So tube is look like a cylinder. Volume of a cylinder is pi r square h. But because the tube is the same tube before and after, so we can just cancel off the pi and the r square because we are using the same tube. V1 and V2, they both have pi r square h. I cancel out. So only worry about the height. So V1 is equals to height 1. That's 8 cm, right? Okay. Look at V2. Now, V2 is equals to, the length decreases to 7 cm. So 7 cm. Now, using Boyle's law, again, pressure and volume, P1 V1 equals to P2 V2. P1, 80. V1, 8 equals P2, we want to find that one, and V2 is 7. This one I get what? P2 equals to 91.43. Pressure, same unit as this one, right? So cm Hg. Now, is this the answer? No, it's not the answer. We want the length of the column, right? So this pressure, what pressure is this? This pressure, P2, is a pressure acting on this point here. Point 2, P2, this point. After you add the mercury, the pressure becomes 91.43, which is the pressure of the mercury column plus the atmospheric pressure. Okay? So this, again, 91.43 is the pressure of this mercury column plus the atmospheric pressure. So don't forget the atmospheric pressure. So if I want to find only the mercury column, then I take 91.43 cm Hg. I take away the 76 cm Hg, the atmosphere. What do I get? Minus 76. I get 15.43 cm Hg. This is the pressure that is only from the mercury. This is the mercury pressure. The pressure resulted in the length of the mercury here. So what is the length of the mercury? 15.43. Means this is 15.43 cm. So your answer is A.